Hi everyone, I'm Kenny Brown, and I, along with my partners, Brynn Browning and Cole Baker, will be presenting to you how waste eggshells can be used to improve polymer properties, reduce non-renewable resource use, and save money for polymer product manufacturers. Much of the polymers around us are modified with additives. These additives can be used to accomplish a variety of desired changes to a polymer's properties, such as increasing strength, stiffness, making plastics more flexible, imbuing conductivity, reducing ultraviolet degradation or increasing wear resistance, and much more, even beyond that. Additives are often broken down into several categories, which include plasticizers, antioxidants, stabilizers, slip agents, and what we'll be talking about today, fillers. Fillers are a very common set of polymer additives that are employed for two main purposes. First, as their name implies, they're used to fill plastics. Fillers are used to replace up to 70% of expensive petroleum-based polymers with low-cost organic or inorganic materials. Many types of materials can be employed as fillers, which creates the opportunity to modify the plastic's properties in the process. It has been shown that some fillers can increase mechanical properties of the plastic or introduce special properties such as conductivity or flame retardants. For example, talc is a very common filler because it is cheap, plentiful, and low density. It is used in many common plastics. For example, it is used to increase the stiffness of polyethylenes and nylons and can be used to make up as much as 40% of polypropylene-based automotive parts. A couple other interesting examples are aluminum trihydrate, which is most commonly used as a flame retardant filler, and magnetite, which can be used to greatly increase electrical conductivity and make plastics opaque to X-rays. One filler of special note is calcium carbonate, which is the most common filler in polymers. Calcium carbonate makes up over half of the total amount of fillers used in the plastic industry. You may be most familiar with this material by way of the popular antacid Tums, for which it is the main ingredient. But it turns out that it is also a key ingredient in everyday plastics, such as PVC pipes, where it reduces the cost of the product while increasing stiffness and impact resistance. Calcium carbonate finds applications in a variety of polymers in addition to PVC, such as polyethylene, polypropylene, various rubbers, and beyond. However, despite its ubiquity, a better option has come to light. Recently, eggshells have been explored as a bio-renewable alternative to inorganic calcium carbonate. Turns out that 95% of an eggshell is calcium carbonate, which makes for an attractive opportunity to turn a waste byproduct into something more valuable. Furthermore, eggshells have a lower density than calcium carbonate, which may be advantageous, for example, in automotive applications by reducing vehicle mass and thus improving fuel economy. Eggshells as fillers have also been shown to be superior to inorganic calcium carbonate at improving the mechanical properties of some polymers. And this is all exciting, but you might be wondering, how do fillers, and eggshells specifically, accomplish these feats? Fortunately, our partner Cole is here to tell you more about the mechanisms behind eggshell fillers. Take it away, Cole.
Thank you, Kenny. I want to start off by giving a quick overview of how these polymer filler composites are made, their mechanical properties, and then move on to what the eggshells themselves can offer as a polymer filler. So these polymer filler composites are generally prepared using melt extrusion with a twin screw extruder system. The polymer and the filler are fed simultaneously to a hopper. And the two screws actually provide a pretty significant amount of shear force, which allows for good dispersion of your particles throughout the polymer. Then the composite is extruded through a die or into a mold to form whatever product you want out of the composite. So we've got an image of one of these composites up here on the right. This is an SEM image of a polyethylene and calcium carbonate composite. We can see there's actually a pretty good dispersion of the calcium carbonate particles. However, there is a very large size distribution, which means that we're seeing some sort of agglomeration here, which is interesting, and I'll talk about this a little bit later as well. But overall, the mechanical properties of your composite are generally in between that of your filler mechanical properties and your polymer mechanical properties. This is an intuitive application of the rule of mixtures, which I'll also discuss in the next couple of slides. So you can make specific modifications to your polymer based on the particle size, the particle shape, and the chemical composition of your particle, which plays a role in the molecular interactions with the polymer. So it's very common to modify the surface of your particles with some sort of chemical in order to increase this bonding and or reduce particle agglomeration, which is also important for mechanical properties, as I'll discuss later. So the mechanical properties of your composite that are important are generally your Young's modulus, your tensile strength, and your impact strength. For this presentation, we'll be focusing on Young's modulus, as the theory for strength and strain is significantly more complicated. But just to round it out, we have 3 different kinds of strength we can look at for polymers. We have our yield strength, which is some strength at a set amount of deformation past our elastic region. We have our ultimate strength, which is basically the peak of that stress strain curve for a ductile polymer. And we have our failure strength, which is where the material fractures. So some of these values can actually be the same depending on what polymer you're looking at. For example, for a polymer single crystal fiber, we actually have, all we have is a failure strength. And so there would be no ultimate strength in this case, or they would all be the same. Something interesting to note here is that impact strength is a very big concern of polymer filler composite manufacturers, as a filler is generally much harder than the polymer you're using. And so it can really have a large impact on your impact strength and actually greatly increase it. So this is basically the energy that a material can withstand for fracture. And as the name implies, it's usually tested by impacting your composite with some certain testing mechanic. So here is some of the generalized theory for polymer filler composites. This is a really broad overview of 2 main assumptions we can make in order to get a model for the Young's modulus. On the left here, we have the uniform strain assumption, which, as the name implies, assumes that the particles in the polymer are undergoing the same strain. And so that gives us the rule of mixtures, where the Young's modulus is equal to the weighted average of the polymer modulus and the particle modulus. On the other hand, we can assume that the particles in the matrix are undergoing the same stress, and that gives us more of a parallel rule of mixtures, something similar. It's also a weighted average of the polymer and the particle filler modulus as well. So these models both assume uniform behavior of the polymer and the filler, which never happens in reality. They also assume perfect adhesion of the particles to the polymer matrix, which again, as you can imagine, is very difficult to achieve in reality. Something interesting to note is that we always look at volume fraction rather than weight fraction for polymer filler systems. So you want your filler particles to be lightweight, as generally a lightweight composite is more desirable than making something heavier. So in the 1940s, Dr. Guth actually developed a much more realistic model of Young's modulus based on filler volume fraction. And this incorporates something called the particle shape factor, which is essentially your particle aspect ratio, which tells you how much surface area of your particle itself is interacting with your polymer matrix. And so the higher the shape factor is, the faster your composite modulus is going to increase. And we can see that in the graph I've made here on the right of the 2 idealistic theories and the Guth model. And we can see with that quadratic term as well, as your volume fraction of your filler gets larger and larger, this quadratic term accounts for particle alignment at high filler loading, which states that as you increase your filler volume fraction, the particles are going to start interacting with each other rather than just with the polymer. And this results in a pretty sharp increase in your Young's modulus. And so this is the model that almost everyone has adopted for polymer filler composites, and it's the model we'll be looking at today. So the first paper I want to look at is a paper in which the authors examine the effects of eggshells and inorganically derived calcium carbonate in common rubber. This is an elastomeric material. They also did a chemical surface modification of both materials before using them as a filler with a terpolymer. So this is a surface modification. And then they analyzed the tensile properties of all four composites, right? So they have the modified and unmodified inorganic calcium carbonate particles and the eggshell particles as well. So they applied Guth's model and used a shape factor to fit their Young's moduli. It's kind of interesting here, they used shape factor to incorporate those polymer, terpolymer, and filler interactions here. So it's kind of a fudge term. It basically accounts for a lot of microscale mechanisms that are going on in these composites. But the conclusion here is that an increase in shape factor results in an increase in tensile, a faster increase in tensile modulus with your volume fraction of filler. So you can see here on the graph on the right, the inorganically derived calcium carbonate did not respond well to the chemical treatment. In fact, the modulus decreased by quite a bit. However, the eggshells responded very well to this chemical treatment. And those composites actually saw an increase in tensile modulus. So the authors attribute this to intermolecular bonding between the eggshells, the chemical surface modification, and the rubber itself. Right, so you can see in this diagram down here on the right, they are stating that there were only van der Waals forces between the unmodified calcium carbonate and the rubber, whereas the chemically modified eggshells, they believe, actually promoted hydrogen bonding and covalent bonding between the functional groups on the eggshell surface, the chemical surface modification with the terpolymer, and the rubber itself. So there's a lot of bonding going on here. And again, for the unmodified eggshells, they've drawn a diagram down here on the left. They're just stating that the proteins on the eggshell surface interacted with the nitrile groups on the rubber, which is why, without that covalent bonding, that they saw a lower tensile modulus for the untreated eggshells rather than the modified eggshells. So the conclusion from this paper is that eggshells offer more room for modulus improvement as a plastics filler than inorganic calcium carbonate. So in the second paper I want to look at here, the authors did something very similar, but for polypropylene, which is a thermoplastic. So they did a chemical modification with isophthalic acid, and they noticed that the chemically modified eggshell composites had an improved tensile modulus over the inorganic calcium carbonate filler. The authors actually attributed this to less agglomeration of particles that had the chemical modification. So basically electrostatic forces between the functional groups on the surface of the particles allowed for better dispersion of the particles throughout the polymer. And this manifests itself in the tensile strength. As if you have less agglomeration, you're going to have fewer defects in your final composite and fewer voids and a higher tensile strength. And you can see here on this modulus graph on the right, the chemically modified eggshells perform the best out of the 3 different composites they manufactured. So in order to back this up, the authors took transmission electron microscopy images of the 3 different kinds of particles. Images A and B here are the unmodified calcium carbonate and eggshell particles. And we can see there's pretty significant particle agglomeration in those 2 images. again, which will show itself as a decrease in tensile strength and a decrease in tensile modulus as well. So in images C and D here, these are the eggshell particles that incorporate a chemical modification. And what we can see here is that the particles tend to repel each other, which tells us that we're getting less agglomeration in our final composite, which is going to give us better dispersion and a higher tensile strength. Something interesting to note here, though, is that the particle shapes are all slightly different, which again, going back to that shape factor from Guth's model, is going to give us a different tensile strength regardless of the chemical modification we put on these particles. So to kind of conclude, eggshell-based composites do have the potential to outperform inorganic calcium carbonate composites in terms of tensile modulus and tensile strength. And eggshells especially seem to respond better to these different kinds of chemical treatments, which the authors of the two papers I presented attribute this to interaction between the chemical modifications and the proteins present on the eggshell surface, which is something that isn't there in inorganic calcium carbonate fillers. Again, these chemical treatments can also reduce particle agglomeration, promoting better dispersion, which will give you an increase in your mechanical properties and a reduction in defects. However, this research is not complete, and I think that more is needed in order to directly compare eggshells and inorganic calcium carbonate, where there are more parameters kept constant throughout the study. And with that, I would like to pass it over to Brynn to discuss the environmental and economic impacts that eggshell fillers can have.
Thank you, Cole. To start, I will review the environmental aspects of making eggshell waste into a resource. Firstly, as with any valorized waste, it will no longer take up excess space in landfills. Space in landfills continues to become an increasing commodity as global consumption of non-degradable and single-use material increases. When eggshells are used as a filler and/or additive in materials, it is also reducing non-renewable waste volume in landfills. The three leading egg manufacturing countries, the USA, China, and India, produce approximately 8.5 million tons of eggshell waste per year. And this amount of waste only increases as global consumption of eggs are predicted to increase. Additionally, eggshells as waste in landfills comes with hazards of increasing concern. Eggshells will attract vermin to landfills and encourage fungal and bacterial growth. As explained previously, eggshells have plenty of potential as filler in plastics, but also have value in other applications such as cosmetics, supplements, cements, wastewater treatment, and as a soil additive. Most applications that eggshells are sought out for are because of its high calcium carbonate content, about 94%. Traditional calcium carbonate is often derived from limestone mining, a process which has a two-step environmental impacts. Firstly, mining damages the local ecosystem's biosphere and aquaculture and leads to the degradation of the land, water, and soil around it. Secondly, processing the mined limestone is a water and energy intensive process. The finer and more pure the material, the more energy and water required to create it. There's also an economic argument to be made for using eggshells waste as a resource. Economic cost comes hand in hand with environmental cost when it comes to eggshell waste disposal. It costs the US alone $100,000 per year per plant to dispose of eggshell waste. And these costs continue to rise for the same reasons that eggshell waste are environmental hazards: space commodity of landfills and biohazardous nature of eggshells. It's easy to imagine that materials like eggshells that can breed bioborne illnesses may see an additional jump in price of disposal in the future. Finally, eggshell waste as a filler in plastic stretches the material value and lowers the cost while increasing mechanical performances of the plastic. This is not only true for examples 1 and 2 shown earlier, but also biodegradable plastics such as starch or chitosan-based plastics as well. Eggshell as a calcium carbonate filler hits a sweet spot of being potentially cheaper than participated calcium carbonate while being higher in quality than ground calcium carbonate.